So how do we actually use the limit definition of a derivative to solve for the derivative? Well, we know that the derivative tells us the instantaneous rate of change at any given point on the graph. So we have two different things that you might get out. First of all, you might get asked just for f prime of x. Remember, this means what is the derivative? And f prime of x basically means give me a function that is in terms of x, right? It'll still have an x in it, that I can put any x value in it and it will tell me the instantaneous rate of change at that exact moment. So f prime of x is going to be a function still. It's going to have some kind of x in it, probably. But you might also be asked for f prime of a number. So that means what is the instantaneous rate of change at this exact point? So this says tell me the derivative when x equals -3. So the first one is going to be some type of function. The second one is going to be a number because this is telling you the slope of the tangent line at that exact point. Okay, so let's use the limit definition of the derivative to figure this out. So f of x is x squared plus 2. So the first part of the limit definition of derivative is I need f, make that a little smaller, f of x plus change in x minus f of x all over change in x. Okay, that's the actual limit definition of the derivative. So now I just need to put in each of these things. So remember that this means I'm just going to put x plus change in x inside of this function. Okay, so that's going to be the limit as change in x approaches 0 of x plus change in x squared plus 2. That is f of change of x plus change of x, right? Because I just put this in for x. Okay. Minus f of x all over change in x. Okay, and you're like, okay, so that doesn't get me anywhere. But now we're going to use some algebra to move this through. Okay. So we have the limit as change in x, approaches 0. Now I'm going to FOIL that out, so I get x squared plus 2 x change in x plus change in x squared plus 2, and I should have put parentheses around that, minus x squared, and see how I noticed that I should have put parentheses around that because I should be subtracting all of f of x, which means I'm also going to subtract 2. All over change in x. Ooh, that looks messy, doesn't it? But guess what? Look, x squared and x squared cancel each other out. And 2 and -2 also cancel each other out. So we're getting somewhere. So we have the limit as change in x approaches 0 of 2x change in x plus change in x squared over change in x. Okay, well looky there. Every single one of those has a change in x in it. Can't we just divide that out? Yes, we can. Because if I tried direct substitution right now, I said the limit as change in x approaches 0, I would put 0, 0, 0, and I would get 0 over 0, which is the indeterminate form. So I can't do that, right? I need to simplify this. So if I divide each of those by change in x, that goes away, and one of those goes away. So I end up with the limit as change in x approaches 0 of 2x plus change in x. Okay, now I can use direct substitution, can't I? I can say, all right, I'm going to put in 0 for change in x. And what happens? Well, when this goes to 0, that's going to go away, and this is just going to be 2x. So the limit as change in x approaches 0 is just 2x, which means this is our derivative. This is f prime of x. So what I'm telling you is that I could put any number into this function for x, and it would tell you the slope of the tangent line at that exact moment on our original function. Yep, that would work. So this next question asks, what is the derivative at -3? So that says, hey, now you found the derivative, which is a function. Tell me what that derivative is equal to when x equals -3. So what is the slope of the tangent line on this curve when x equals -3? So all we do is we plug -3 in to here. So f prime of -3 equals 2 times -3. So f prime of -3 equals -6. So the slope of the tangent line on this curve when x equals -3 is -6. Now you know what this curve looks like. This is a parabola that's shifted up to, and that makes sense, right? If you think about a parabola that's shifted up, when x equals -3, we're somewhere around here, and so I can't even get my line to get there. You've got some line like this, right? It makes sense that the slope of that line is negative, and it makes sense that this slope would be a really steep negative number. So yeah, absolutely, that totally makes sense. You don't have to graph this, and you don't have to visualize the graph, but sometimes it helps you to see if it makes sense. All right, let's calculate another derivative. Here is a function, and it asks for y prime. Remember, y prime is the same as f prime of x. It's the same as dy dx. It's just another notation. So let's use the h notation this time instead of the change in x notation because it's a little less messy. So y prime equals the limit as h approaches 0 of f of x minus h, plus h, f of x plus h minus, see, I was getting ahead of myself, f of x all over h. So now I just plug these in. So that's equals the limit as h approaches 0. What is the function? Well, the function is the square root, and instead of x, it's going to be x plus h minus the square root of x all over h. Okay? Now, if I put h equals 0 in here, I would have 0 in the denominator, so that's a problem. So how do I undo that? How do I actually get rid of that? Well, if you remember, we're going to multiply by the conjugate. So we're going to multiply top and bottom by root x plus h plus root x. And that's going to get rid of those square roots on the top. So on the top, we end up with the limit as x. See, we haven't evaluated the limit, so we have to keep reminding ourselves that we're still doing the limit, so you have to keep the limit notation there. So we get x plus h minus x plus, the middle terms cancel out, minus x, because root x times root x is root x squared, which is just x, all over h times x plus h plus root x. Okay, so now what do we do? Well, if you look at the top, you see that this is x plus h minus h, so those x's actually cancel out. And we have the limit as h approaches 0 of h over h times all that business. Okay. And then you see that you have an h on top and you have an h on bottom. Awesome. So, again, we still haven't evaluated this limit, so we have to keep writing the limit as h approaches 0. You have to write that every single time if you haven't evaluated the limit yet. Okay. So here I am. I've simplified it all the way down. And now I can say, okay, when h approaches 0, as h gets really, really, really close to 0, that gets really close to just root x, right? So I get root x plus root x, which, so if you think about as this approaches 0, it disappears. So I end up with 1 over 2 times root x, because I have root x plus root x. So this is the derivative of the original function, which tells me if I put any value in for x, I will get out the slope of the tangent line at that specific point. So we have another function here that is with respect to t. So instead of using an x, we're using a t. It's no different. It's just anytime we saw an x before, we would just now put a t in. And if you notice the notation here, we have f prime of t, and then we have dy dt. Notice when we're taking the derivative with respect to a certain variable, we need it to be dy dt, whatever variable it is on the bottom. And that's super important as we get further into calculus. I know it seems really nitpicky right now because it's like, well, duh, we're taking the derivative. But there are times when we're going to take the derivative of different variables. So anytime I had an x, now I'm going to have a t. So I have the limit as h approaches 0 of f of t plus h minus f of t over h. So let's just go ahead and plug this in, though. We have the limit as h approaches 0 of 2 over t plus h minus 2 over t all over h. Okay, so now let's get a common denominator on the top. So since I still haven't evaluated my limit, I still need to just write the limit as h approaches 0 because I'm still evaluating it. So to get a common denominator, I need to multiply the top and bottom of that one by t. And I need to multiply the top and bottom of that one by t plus h. Okay, and that's all over h. And so now I can put those together, right? So I have the limit as h approaches 0 of 2t minus 2t minus 2h, because I just did the math, I just multiplied things in, all over t times t plus h, all over h. Ooh, that's ugly, isn't it? Okay. So we notice that I have 2t minus 2t, so those go away. Then we rewrite this as the limit as h approaches 0 of negative 2h over t times t plus h, all over h. Ooh, that didn't work so well. All over h. And this is so ugly that I'm just going to get that h out of the denominator. Remember that dividing by h is the same as multiplying by 1 over h. So all I'm going to do is bring that h up, and now it's abundantly clear what I need to do. I have an h on the top, and I have an h on the bottom, don't I? So I still haven't evaluated my limit, so I have the limit as h approaches 0 of negative 2 on top times t plus h on bottom. And so now what happens as h approaches 0? I no longer would have a problem. I would no longer have an indeterminate form or anything like that. So I can just say, okay, as h goes to 0, that's just going to disappear, right? And so then what do I end up with? Well, I have negative 2 over t times t. So I end up with negative 2 over t squared. And that, my friends, is the derivative of 2 over t.